Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we started discussing about surface tension. We saw what is exactly surface tension and many more terms related to surface tension. What is intermolecular force of attraction, cohesive force, adhesive force, and molecular range and sphere of influence, something like that. So we saw a lot of things related to surface tension. Let's continue here, and we also discussed that final what is exactly surface tension. So it's basically property of liquid at rest where its free surface of liquid is behaving like a stretched membrane. We call that property of liquid as surface tension. We understood it from molecular theory that at molecular level how this property actually arises. So that is because the molecules which are lying on the surface are having net inward force. Because of that, there is one more tendency that the molecule or liquid always try to have minimum surface area, right? So that is about surface tension we discussed in the last class. Let's talk about factor affecting surface tension of liquid. So here there are many factors, but we will talk mainly about two, that is temperature and impurities. Okay, so first thing to understand how temperature affect that, how exactly surface tension, I mean, like, what is the reason for surface tension? The reason for surface tension is intermolecular force of attraction. So now you need to relate the intermolecular force of attraction with the temperature. So if we are increasing the temperature of a liquid, then what happened to the intermolecular force of attraction? You must be like, when we are heating, right, water after some time start boiling. Why? Because initially at low temperature the molecules of water are bonded strongly, and that's why the water molecules are not able to go outside in the air. And when we are heating, molecules are getting higher energy, and they are having more energy, means they are capable to break that bond, that they are capable to break that intermolecular force of attraction easily. So what it means effectively I can say, as we are heating, the intermolecular force of attraction, effective intermolecular force of attraction goes on decreasing, and intermolecular force of attraction is the reason for surface tension. So what it implies, that means I can say, as we are heating, effective intermolecular force of attraction will decrease, and that implies surface tension of liquid will also decrease. So surface tension of liquid decreases with rise in temperature, is it? So surface tension of liquid decreases with heating, or you can say rise in temperature, right? So as we are heating, the temperature rises, surface tension. The reason you can relate is that as temperature rises implies molecule kinetic energy increases, so the effective intermolecular force of attraction, we can say it become like less strong, or I will write it decreases. And we know higher is the intermolecular force of attraction, higher will be the surface tension. So as temperature rises, kinetic energy increases, that result in effective decrease in intermolecular force. So that's why we can say surface tension of liquid decreases, and we can write at boiling point surface tension of liquid become 0, or we call a critical temperature at which surface tension, or at critical temperature. Critical temperature is that temperature at which surface tension becomes 0. Temperature surface tension of liquid becomes 0. And we can relate for small temperature, we can write surface tension T is equal to T naught 1 plus alpha delta T, is it? Or I will write better theta, where alpha is the coefficient of surface tension. Okay, so here where T is surface tension, first let me rearrange it a little bit. So T can be written as T naught 1 plus alpha, this can be written theta minus theta naught, that is actually like 0 degrees Celsius. Then it comes T is equal to T naught 1 plus alpha theta, where T is surface tension of liquid at theta degree Celsius temperature. T naught is surface tension of liquid at 0 degree Celsius temperature. Alpha is called temperature coefficient of surface tension, right? So this is the relation of surface tension with temperature. The logically point is you must understand why actually with rise in temperature surface tension decreases, because we can connect surface tension is mainly because of intermolecular force of attraction, and we can easily correlate intermolecular force of attraction with the temperature. Temperature rises, intermolecular force of attraction decreases. And the next factor which affect the surface tension is called impurities. Okay, so the next factor affecting surface tension of liquid is impurities. Again, we can think about impurities also. So there can be two types of impurities. And what exactly happening here is impurities are ultimately also affecting the intermolecular force of attraction. So how like they can like affect in different manner? The thing is that if there is a one type of impurities which is increasing the intermolecular force of attraction between molecules even stronger, what we can expect? The surface tension will increase, right, based on those impurities. Another impurities which are making this intermolecular force of attraction even lesser or less stronger, we can directly say that they will decrease the surface tension. Now the point is like which will increase the surface tension or which will increase the intermolecular force of attraction. So these we can relate with the help with the concept that whether it's soluble or not, because solubility, if you understand it in your chemistry part, like then like when intermolecular force, if they are like is it mixing, means like getting dissolved, means molecules are attracting more, is it, then only one substance will be soluble. If the molecules are not like attracting, is it, they are repelling, then they will separate, they will not mix actually. So mixing is related to intermolecular force of attraction, understanding. So if the molecular force of attraction is stronger, it will mix even better, right? So that's why we can say impurities, I can write all the better soluble impurities, we can say make intermolecular force of attraction stronger and So surface tension of liquid will increase. Example, NaCl, salt in water. So NaCl is like highly soluble, increases the surface tension of water. Similarly, next case, you can say sparingly means less soluble. Impurities make intermolecular force weaker so these impurities reduces the surface tension of liquid. Right, so all the impurities which are less soluble, sparingly soluble, they will reduce. Example here, phenol. It's like less soluble actually comparatively. So in water decreases the surface tension of water. So these are the factors which mainly affect the surface tension. So one is temperature. Temperature increases, surface tension of liquid decreases. Another factor is impurities. In impurities, there are two cases. Soluble impurities will increase the surface tension. Insoluble or less soluble impurities will decrease the surface tension. And we can correlate that with the intermolecular force of attraction for liquid. Okay, next is surface energy. What is that? Surface tension we understood. Now see, like all the molecules which are lying on the surface, you must be clear by the time that these molecules which are lying on the surface are experiencing net downward force, is it? So if we want to increase the surface area, then what we need to do actually? We need to pull the molecules from the interior on the surface. That means you need to do some external work against the intermolecular force of attraction to bring a molecule from interior of the liquid to the surface. So there we need to do some external work. So this work done by external agent will store in the surface in the form of surface energy. Understanding? So you must be clear that where exactly we have to do some work. So here we can say, right, the molecules on the free surface experience net downward force due to intermolecular force of attraction by other liquid molecule. So to bring a molecule on the surface, on the free surface from interior of liquid, work need to be done against this intermolecular force of attraction. This work done by external agent per unit surface area will store in the form of potential energy of surface, and this potential energy per unit area is called surface tension. Let's calculate it. What will be exactly numerically it's equal? So consider here a wire frame like this, A, B, C, D. So consider a wire frame A, B, C, D, and let me consider one movable sliding rod, let's say L, M, okay, which can be freely slide without friction. Now what I'm doing is I'm taking this and dipping this in the soap solution. So dip this system in soap solution. What will happen? A layer of liquid will be formed on this. So this is your soap film, right? Means liquid surface. So now if its length is, let's say, L, and surface tension of soap solution of soap solution is, let's say, T. So first thing is simple. Now because this is a free surface of soap solution, so it will have tendency to contract, to reduce its surface area. So because of that, on this wire there will be net inward force acting, which will try to reduce the surface area. To just keep it in balance, we need to apply some force F, right? Otherwise it is free to slide, it will simply move and this area will keep on increasing, keep on decreasing. So F is the force need to keep in balanced. In balance, right? Because otherwise net, okay, now one point here is that you need to understand what will be that force. It will be, F will be T into L or T into 2L, right? The force F will be equal to T multiplied by 2L. I hope you must be clear here why it is T into 2L. Let me just erase this part. The thing is that this soap film will have two surface, because this thickness, if you just look at this, is, let's say, soap film, so this is your wire LM, then this soap film will be like it will be like this, because it will not be, the thickness of this layer will not be just simple one molecular layer, molecular thickness. It will have some thickness. So one surface area will be up, another surface area will be down. Let's be, then this will be, and it will be your, so this is upper surface, lower free surface, and this will be upper free surface, and this is your LM rod. So here net some T force will be acting, surface tension T will be acting downward. So that's why net force acting on this will be like, this will be total will be, I can write F down this side will be equal to T multiplied by L here. So this is 2L. I hope you must be clear that why F will be equal to T into 2L, because this is your wire. So the film will be like this. One is top free surface, another is bottom free surface. So these molecules will be pulling and these molecules will be also pulling it. So to balance it, you need to apply this much amount of force. So this is the situation, right? Now, so to just keep it in balance, we need to apply this much amount of force. But if, is it? The rod LM is pulled slightly by distance x right side, then what will happen? Force we are applying, displacement is there, this is shifted, let's say up to here, this distance is x. Then what is the work done? Work done by force, W can be written as force into displacement, that is equal to F is equal to T into 2L into x. This is equal to T into 2Lx. And what is this? 2Lx, I can write total increase in surface area. 2Lx is, let's say, delta A, total increase in surface area, right? So this is work done, and this work done, where it is going, right? This work done will store in this soap film in the form of surface energy, right? So this work done will store in the form of surface energy, right? So means if we want to increase the surface area, we need to supply some amount of energy. If energy is not supplied from outside, then it will be consumed from the liquid inside, and that will appear like with the reduce in temperature, because if energy is getting consumed means then its temperature will fall, and vice versa. If its area is shrinking, then it will release some amount of energy, and if it is not released outside, then it will be utilized by the liquid by raising its temperature, right? So the thing is that you must be clear that why when we are increasing the surface area, work is needed to be done, because we are bringing more molecules on the surface. That means we are pulling those molecules from the interior, and when we are pulling, we need to apply some force, because intermolecular force of attraction is pulling them down. So to pull them, counter that, we need to apply some force. Force multiplied by displacement will be some work done, and this work done, because no kinetic energy change is there, so it is getting stored in the form of surface energy, is it, or in the surface. So first thing is this, I can write surface energy, is it? So del W, or let me write it surface energy, then this is equal to T multiplied by delta A, and this implies surface energy or tension can be written as surface energy divided by delta A. So tension can be also written as, it is equal to surface energy per unit area, right? Amount of surface energy required to increase the area by unity is also called surface tension. Surface tension it is also defined as amount of surface energy required to increase the surface area by unity. Energy for surface energy, like unit for surface energy will be simple joule. So here we can calculate that this is the force to displacement, then force into displacement will be work done, and that comes out with this is the change in area. 2Lx is the change in area, total increase in area, and this is right. So we can, one more thing, surface tension does not depends here on area, because you can see like the force, if I'm increasing the length, then only the force on these, because number of molecules will increase. So surface tension, from here you can say, you might be thinking surface tension is inversely proportional to area or maybe directly. No, it's not actually. Surface tension does not depends on area. Let me write it in. Surface tension does not depends on the area, right? Even surface like force also, it depends only on length, is it? Force that we need to, like, that is equal to, force is equal to T into L. So if higher is the length, more will be, like, more molecules will be attracting, that's why more force will be required, is it? So this we can define surface energy. And so means when we are, surface area is getting changed, there will be surface change in surface energy, is it? So here, if surface area is increased, means energy must be supplied from outside. If it is not supplied, then it will result in reduce in temperature or reduction in temperature, is it? If not supplied, then will be consumed from liquid and result in decrease in temperature of liquid, and vice versa, is it? So this is about surface energy. Let's see. So here, if spray, you know, actually, so in case of spray, what we do actually, we are like, liquid is there and we are making small droplets. In that case, we are increasing the surface area, and when surface area increases, then it's consuming energy from inside, and that's result in cooling of liquid actually. So that's why when we are spraying, it appear cooled, actually it appear like colder actually on the skin. That is because in increasing the surface area, it's using energy from inside, and that result in reduction in temperature. Let's calculate that amount of like energy required or energy changes when area is changing. Okay, so we understood actually surface energy, that like all the molecules lying on the surface, they have net downward force. If we want to increase the surface area, then we need to pull molecules from the interior of liquid to the surface. So there some work is needed to be done, and then we spend some amount of energy, and that energy is getting stored in the form of surface energy. So let's see some like application of it. So work done in blowing a soap bubble or liquid drop. So in this process, what exactly we are doing? So let's say we are having liquid, is it? And from that we want to generate we want to blow a soap bubble. In that process, what is happening? We are creating some additional surface, is it? So whatever the surface we are creating, for that we need to supply some energy. That energy will be the energy required, or that will be like work done in blowing a soap bubble and liquid drop. So let me just first liquid drop. I mean, like, you need to understand how you can apply the concept of surface energy in such cases. So even problems are also formed, like asked based on similar concepts. You will be able to solve once you are understanding this. So now we are having initially liquid, and from that we are making a liquid drop. So in drop, let's say of radius r, and surface tension of liquid is let's say T. Then how much surface area has been increased? I'm like created, is it? So let's say this is a drop, radius, surface tension. So then work done, I can write this is initial, because I am creating it, I'm blowing it from liquid. So I'm taking like its free surface is still remaining same. So from the deep inside liquid, we are forming this drop. So then the increase work done will be equal to what? Surface area multiplied by tension, because we understood just now, is it, in the concept of surface energy. So that can I can be read delta A multiplied by surface tension will be the work done, and delta A is change in surface area. So final you can write this is equal to 4 pi r square. Initial you can take it 0, because we are creating this drop from the liquid. So delta A you can write this is equal to 4 pi r square. Then I can write work done is equal to 4 pi r square multiplied by T. So this is the amount of work done in blowing a drop, liquid drop. Similarly, for a soap bubble, so for this case you need to understand the difference between a bubble and drop. So what is the difference between bubble and drop? Drop means when it is from inside it's filled with the liquid. Bubble means there is inside also air is filled and outside also there is air. So in case of bubble, we are creating, or basically the surface area is higher. You need to understand this, is it? So in this is a bubble, so then air here and inside also there is air, and its thickness we take very small. So let's say R. Then how much, what is the total surface area of this bubble? So one is inside, another is outside. So total surface area A I can write 4 pi r square plus 4 pi r square. Then work done is equal to A multiplied by T, and that is equal to 8 pi r square multiplied by T. So this is the work done in blowing a bubble. Work done in blowing a soap bubble is equal to simply 8 pi r square into T. You must understand that why and how like this much work will be done and where exactly this work done is going. So these are simple concepts, simple application of surface energy. Okay, so similarly there are many possibilities actually where we can talk about work done in increasing the surface area of a bubble, a drop, is it? So one case is work done in splitting a bigger drop to n small drops, is it? So here what is happening, we are having one bigger drop. Let's say this is a bigger drop of radius capital R. Surface tension of the liquid is T. It's being splitted into n small drops of small radius R. These are all overall n drops. So in this situation you can easily imagine what exactly happening. This bigger drop is splitting, we are increasing the surface area of free surface area. Simply that increase, change in surface area multiplied by the tension will be the work done that we need to do additionally, is it? So we can calculate here. So first, because we don't know what is the radius R, so we need to get the relation for radius R. How we will get that? That is by conservation of volume, is it? Because when the drop is splitting, volume is remaining constant, is it? So first kT R by volume conservation. That means 4 by 3 pi capital R cube must be equal to n multiplied by 4 by 3 pi small r cube, right? So 4 by 3 pi gone, and we imply this is capital R is equal to n power 1 by 3 into small r, or you can write small r is equal to capital R divided by n power 1 by 3. So this is the relation between small r and capital R. Then what is the change in surface area? I will write change in surface area, that you can write will be equal to total A final minus A initial, and that is equal to A final is n multiplied by 4 pi small r square, initial is 4 pi capital R square. So this is the change in area, surface area. We can get the relation in terms of small r, capital R, either one. If you want to substitute capital R in terms of small r, then you can substitute capital R equal to this. If you want to substitute small r, I mean like if you want the final expression in terms of capital R, then we will substitute small r. So substituting it there, we are getting n. It will let me take 4 pi also out, so small r, then it's r square divided by n power 2 by 3 minus r square, and n taking inside and taking this is 4 pi r square out, and it will be n will not be here, it should be here, is it? Because it's only in multiplication here. So then it can be written as n power 1 by 3 minus 1. So this is your change in area. Then work done will be equal to what? Done in splitting the bigger drop, that can be written as work done is equal to delta A, change in area, multiplied by surface tension, that is 4 pi r square n power 1 by 3 minus 1 into T. So this is the work done in splitting a small bar, like a bigger drop to small drop. Okay, next things comes is that sometimes let's say this is the additional energy we need to supply. If let's suppose outside, I mean like no energy is supplied from outside, then what will happen actually? This same amount of energy will be used from the liquid itself, from the volume of liquid, is it? Whatever is available. So that means it will cool down actually. That is one of the reason when like spray is working actually, so it's splitting actually liquid into small drop. In that process, what is happening? Surface area is increasing, so some energy is getting consumed in that, so that result in cooling down of the liquid, is it? So if this energy is not supplied, then it will be used from liquid, and that will result in cooling down of liquid. So then what will be the change in temperature? How much temperature will drop? So this is the amount, is it? So if I say if m is the mass of liquid, S specific heat, and let's say change in temperature is delta theta, then what I can write? Q is equal to what? Ms delta theta, and the mechanical equivalent of this heat, I can write W equivalent will be equal to J multiplied by Q. J is mechanical equivalent of heat, and that comes out to be J Ms delta theta. Now this quantity should be equal to how much? This. So this implies J Ms delta theta must be equal to W must be equal to 4 pi r square into T n power 1 by 3 minus 1. So just rearranging it, I can get the expression what will be the drop in temperature of liquid on splitting a bigger drop to smaller drop or n smaller drop, is it? So that implies the change in temperature of liquid, that can be written as, by just from there I can write delta theta is equal to 4 pi r square into t n power 1 by 3 minus 1 divided by j m s. This is the drop or change in temperature. Here J is called mechanical equivalent of heat. So I hope you are getting it. Simple terms, wherever something is asked to you regarding the surface energy, your focus must be on the change in surface area, is it? Because you must be understanding it at even molecular level, at atomic level. When surface area is increasing, more molecules we need to brought on the surface, and all the molecules on the surface is having net downward force. So if you want to brought one molecule of liquid from deep inside to the surface, work need to be done, and that work is stored in the form of surface energy. So depending on if it is supplied from outside, then the temperature of liquid will remain constant, and you need to supply this much amount of energy if you want to break down a bigger drop to small n drops. And vice versa also, there may be another possibility that we are combining n small drops to one bigger drop. In that case, what will happen? Energy will be released, and that will be just reverse process. So exactly this much amount of energy will be released, and if it is not actually taken outside, then what will happen? This energy released will be absorbed by the liquid, then its temperature will rise actually. So I hope you will be in position to even calculate that rise in temperature, energy released when n small drops are combining and forming a bigger drop, is it? So let me just consider another case where what we are doing is if we are having a bubble of radius, let's say r, and thickness t, and it's bursting into a drop. So a bubble of radius r and thickness t into a drop. Surface tension of liquid, it's T. Okay, so surface tension of the liquid is T. Then you are asked to find the work done or energy released. So first thing is just think logically, what will be, whether you need to do some work externally or energy will be released in this process. In this process, what is happening? We are having this bubble, okay, and its thickness, this is T, radius, take it R, and you can take actually T is quite smaller than R, it's not very large. So in this situation, when it is burst, is it punctured, check the spelling, then what will happen? It will result in a drop of some radius smaller. How I will get the radius? And we need to get the change in surface area also. That ultimately we will get, once you have surface area change, then multiplied by T will be the energy. whatever, whether surface area, if it is increasing, energy need to be supplied, surface area decreasing, energy will be released. Simple concept, right? So in this process, first by volume conservation, what I can say, initial, what is the volume? 4 pi r square multiplied by thickness. This condition, if T is quite large, then you need to get the volume 4 by 3 pi r plus T whole cube minus 4 by 3 r cube, if this radius is in inner radius. If it is outer radius, then change in volume will be 4 by 3 pi r cube minus 4 by 3 pi r minus T whole cube, right? Simple term. But here, because T is small, so that's why I can write this is the volume of liquid in this bubble, and this should be equal to how much? 4 by 3 pi small r cube, right? So just 4 pi gone. This implies r is equal to 3 T r square whole power 1 by 3. I hope you are clear. We got value of small r. Then what is the delta A? This is equal to 8, because 4 pi r square by considering this condition. So it will be 8 pi r square minus 4 pi small r square. Small r square, I can substitute this. So that is, let's say 4 pi, let me take it out, then it is r square minus, substituting it there, so this is 3t r square whole power 2 by 3. So this will be your net change in surface area. Then work done, or basically here surface area is decreasing, so energy will be released. So you can write energy released will be equal to delta A multiplied by T, that is 4 pi T r square minus 3t r square whole power 2 by 3. This will be the result to the problem. So I hope you people must be feeling comfortable with this part. So here simple things is surface energy. You must be clear what is exactly surface energy, what does it mean. Surface energy means molecules, when they are lying on the surface, they always feel net downward force. This is the property of liquid, we call that surface tension. So its tendency is to always have minimum surface area. Why? That too also you must be understanding, because molecules on the surface feel or have net inward force, downward force. So we want to increase the surface area, we need to bring more molecules on the surface. For that you need to do some external work. So now whenever like something is asked, energy released, energy supplied, etc., etc., just go for change in surface area in whatever the process it is happening. Like the case I just discussed, is it blowing a bubble or drop. So in that situation I considered you are like having some tank of water, and from that you are creating one bubble or maybe drop. If we are let's say changing the area or changing the like things, is it maybe let's say smaller bubble to bigger bubble you are blowing, then you need to go for change in surface area, or from small bubble to larger bubble. Logically things must be clear, then I don't think you will have any problem in going any way from any direction. And if you remember things from your heat and mass transfer, then energy supplied is equal to what? I mean like whatever like cooling and heating is taking place, that will be equal to Q is equal to ms delta T. So mechanical equivalent is J, then you can write Q W is equal to Q into J, right? And then that will be like J ms. So this is J, not T actually, where J is mechanical equivalent. So this is different things related to surface energy. Let's see more cases here. Okay, let me do the calculation for formation of bigger drop also. So when we are having n small drops, so formation of bigger drop. So let's say n small drops of radius small r coalesces to a bigger drop of radius capital R. Right, in this situation again what we need to do, we need to consider the change in area. So here you can see n small drops coalesces, is it merges n, and they are forming a bigger drop of radius capital R. Surface tension of the liquid is T. So in this process definitely you must be understanding the surface area is what is happening, decreasing, is it? So energy will be released. So energy released can be written as initial surface energy minus final surface energy, and that can be written as T multiplied, initial surface energy is T multiplied by surface area. So surface area of one drop 4 pi r square, is it, multiplied by n multiplied by T, total initial surface energy, minus 4 pi r square multiplied by T. So this is 4 pi, this you can write T, this is n r square minus capital R square. This is, you can write, energy released. Right, now if this energy is used like not taken outside, then what will happen? It will be used for increasing the temperature, is it? So if this energy is absorbed by liquid, then we can write then rise in temperature. So we can write E is equal to J into Q, that is equal to J into M as delta theta. M is the mass, then delta theta can be written as delta theta, not delta Q, E released divided by J into M into S. E released is 4 pi into T multiplied by n r square minus capital R square divided by J as specific heat into M. M, if you are provided with the radius and density, then you can write it in terms of density and radius also, is it? So mass will be equal to what? It will be like 4 by 3 pi r cube into D, or this is also equal to 4 by 3 pi small r cube into n into D. Either way, with density of liquid. So in that case you will be able to express the result in terms of density also. So this is the amount of, like, this is the rise in temperature of bigger drop, because the energy released in this process is being absorbed by this drop. Next, consider, like, because sometimes problem can be asked to you that no energy is getting lost and not energy released is also not actually consumed or not absorbed by the liquid. Let's say this complete energy released is used by the drop in the form of kinetic energy, then what will be its velocity? So if the total energy released is used as kinetic energy by drop, then what will be its speed? So that we can write what? It's half mv square is equal to what? Energy released, and that is equal to 4 by 3 t multiplied by n small r square minus capital R square. Again you can rearrange it. So v is coming out to be 8 pi t n r square capital R square divided by m under root. This will be the velocity. Depending on what is given to you in the information given to you in the problem, mass, if it is not given straightforward, you can write it in terms of density and volume and so on. If you are given with the, like, let's say n number of drops, small radius is given, then you can get the bigger radius also by just considering taking equal volume for initial and final situation. So these are all different possibilities you can go for, you can check for related to surface energy. So I think like you people should not have any problem in getting the information, getting the relation, getting solving problems related to surface energy. Let's continue from here onward in the next class. Thank you.